Hello everyone, welcome to the YouTube channel E for EMF. This is a control system lecture series of our channel, and in this particular video, we'll learn how to draw a Nyquist plot for type 1 system. So quick recap. What is Nyquist plot? It's an semi-graphical approach to define stability of a closed loop system from the frequency response of open loop system. This Nyquist plot can be drawn for type 0 system where there are no pole at origin or 0 pole at origin. That means they are type 0 system. If there is one pole at origin, as we can see here, then this such system is called type 1 system, and if there are two pole at origin, then that system is called type 2 system, and so on. So let's consider the example number 2, where a loop transfer function of a plant is given to you. You can use the Nyquist plot to define the stability of this closed loop system. Drawing Nyquist plot becomes so easy once you understand few concepts. This Nyquist plot detects the right hand side poles. How it is detecting that Nyquist plot? Uh, how it is detecting the right hand side poles? So how we detect poles on the right hand side using Nyquist plot? We need to first draw this Nyquist plot using some rules. So the first rule is the entire Nyquist plot is divided into 4 parts. Then part 3, it's similar to first part but is in opposite direction or in inverse direction, and it start from infinity. To be precise, it start from minus infinity and goes to 0. So part 3 is where omega varies from minus infinity to 0. And the last part is a semicircle near origin. It is having radius small r. Part 4 is having radius small r e raised to j theta, where r is very small, that is nearly equal to 0, and that theta, that is direction, is going from minus 90 degree to plus 90 degree. So starting from origin, part 1, omega varies from 0, it goes to infinity. Then a right hand is mapped using a semicircle with radius r e raised to j theta, and then the inverse part is mapped of the first part, that is omega varying from minus infinity to 0, and the last part is a small semicircle near the origin whose radius is r e raised to j theta small r, and it is varying from the angle or the direction minus 90 degree to plus 90 degree. So now let's understand how to map this entire right hand side of this S plane to some W plane by using by mapping all part 1, part 2, part 3 and part 4 by using some rule. So let's draw the part 1. So let's draw the part 1. For the drawing of part 1, you need to first put S is equal to j omega into the given transfer function. A quick note that why we put S is equal to j omega and not sigma plus j omega. So in S plane we know S is equal to sigma plus j omega. So it's if the output is varying and it's damped oscillation, and after it's settling down to steady state, so this part is called transient part and this part is called steady state part. So during transient part, we do have some value of sigma, like negative value of sigma, that is it's a damping ratio. But in steady state part, this value of sigma is 0, that the system reaches to a steady state condition and there is no damping, just small oscillations are there with some frequency omega. That's why the sigma value is 0 in this case, and the sigma That's why the sigma value is 0 in this case and sigma vanishes, and we put S is equal to j omega. Okay, after putting s is equal to j omega, we will get the transfer function in this form: g j omega h j omega is equal to 1 upon j omega, 1 plus j omega, 1 plus 2 j omega. Once this is done in step number 1, you can go to step number 2. So next step. In step number 2, you have to find equations of magnitude and phase of the given transfer function. We already know the magnitude of any complex number a plus jb can be taken as square root of a square plus b square, that is square root of real part square plus imaginary part square. So the magnitude and phase of the given transfer function given in equation number 1 can be calculated as magnitude is the determinant of gj omega h j omega is equal to, here in numerator there is no complex number, so real part is only 1 and square root of this square is the same, so we will get 1 in the numerator, and in the denominator there are three complex terms: j omega whose real part is 0 and imaginary part is omega. Second term 1 plus j omega whose real part is 1 and imaginary part is omega. And the third part is and the third number is 1 plus 2j omega whose real part is 1 and imaginary part is 2 omega square. So it can be again resolved as m is equal to 1 upon square root of omega square, that is omega, again square root 1 plus omega square root 1 plus 4 omega square. So this is equation number 2, that is equation of magnitude. So in the next we need to calculate the equation of phase of a transfer function g j omega h j omega. We already know if there is a complex number a plus jb, its phase can be calculated as tan inverse of imaginary part divided by the real part. So using the same technique, we can calculate the phase of the given transfer function. So here in the numerator of our transfer function 1, there is no imaginary part. So tan inverse of 0 divided by real part 1 divided by tan inverse imaginary part omega divided by real part 0 into tan inverse imaginary part, that is omega, divided by real part 1 into tan inverse imaginary part 2 omega divided by real part 1. So I can rearrange this equation as I know tan inverse of 0 is 0 degree, tan inverse of omega by 0, that is infinity, so tan inverse of infinity is 90 degree. And by using rules in polar form, I can write the phase equation of phase equal to 0 minus 90 degree minus tan inverse of omega minus tan inverse 2 omega. So this is equation number 3, that is the equation of phase. So I can neglect this 0 and can write this equation of phi as equation number 3. So once you get the equation of magnitude and phase, you need to vary omega from 0 to infinity and calculate this magnitude and phase for the part number 1. So we are omega equal to 0 in phase equation. The equation is as minus 90 degrees Celsius minus tan inverse of omega minus tan inverse of 2 omega. So putting 0 in this equation, we will putting 0 in the In the place of omega, we will get minus 90. Tan inverse of 0 is nothing but 0, and tan inverse of 2 times 0 is again 0. So minus 90 minus 0 degree minus 0 degree. So we got the value of magnitude and phase at omega equal to 0. Then magnitude and phase at omega equal to infinity. We put the same thing, limit omega tends to infinity. 1 upon omega square root of 1 plus omega square, 1 plus 4 times omega square. So putting omega equal to infinity in this equation, we'll get 1 upon infinity, that is equal to 0. And similarly for phase, limit omega tends to infinity, minus 90 degree tan inverse of omega minus tan inverse of 2 times omega. So here omega, if we put omega equal to infinity, so what we will get is minus 90 degree tan inverse of infinity, that is again minus 90 degree minus tan inverse of infinity 90 degree. So total minus 270 degree. So by putting omega equal to 0, I get magnitude as infinity and phase at minus 90 degree. And by putting omega equal to infinity, I get magnitude as 0 and phase at minus 270 degree. So let's put these points in our graph. So let's draw the Nyquist plot for part 1 by using two obtained points. The first obtained point is at omega 0, that the Nyquist plot will start from 0 frequency and its magnitude will be infinity, and phase is at minus 90 degrees Celsius. So where is minus 90 degree in this W plane? So one thing you need to understand, the positive real axis is at direction 0 degree, and if you measure angle in anti-clockwise direction, then it is positive. So in that case, positive imaginary axis will be at 90 degrees Celsius, negative real axis is at plus 180 degrees Celsius, negative imaginary axis is at 270 degrees Celsius, and so on. Similarly, if we measure angle in anti-clockwise direction, then it is negative. So in that case, the 0 degree will be at positive real axis and negative imaginary axis will be at minus 90 degrees Celsius. Negative real axis will be at minus 180 degrees Celsius and positive imaginary axis will be at minus 270 degrees Celsius. So yeah, we do have point M is equal to infinity and phase at minus 90 degrees Celsius at omega equal to 0, that is starting point of a Nyquist plot. So that minus 90 degrees Celsius is somewhere here, and my infinity magnitude could be here. So let's say that point is somewhere here where omega is 0 and magnitude is infinity, and angle is minus 90 degrees Celsius, right? It's on negative imaginary axis. So the second point, this part 1 of this Nyquist plot will start from omega equal to 0 and end at omega equal to infinity. So at that point magnitude is 0 and angle is minus 270 degrees Celsius. So minus 270 degrees Celsius is here in positive imaginary axis. So the omega equal to 0, this point will start from here. This Nyquist plot will start from here and it will go to magnitude 0. The magnitude 0 will be here at omega equal to infinity, but the direction of the Nyquist plot is coming is minus 270 degrees Celsius. So the minus 270 degrees Celsius is somewhere here. So the direction of plot direction of Nyquist plot will be coming from somewhere here. Okay, so Nyquist plot can start from here and it will go at this point. One thing we got to understand that the Nyquist plot is coming from 270 degrees Celsius. So this direction is exactly okay, that from infinity it's 270 degree. But it is intersecting somewhere to real axis. It may be intersecting to imaginary axis, we don't know. So we need to find out the intersection of the first part of this Nyquist plot with real axis and imaginary axis. So here we can see it is intersecting to real axis to somewhere in this point here, and it is intersecting at imaginary axis somewhere here. So we need to calculate exactly where these are intersecting, otherwise this graph will be incomplete. So how we are going to find out this intersection with the real axis and imaginary axis? So for that we need to separate out the real part and imaginary part of this given transfer function h j omega g j omega. So given transfer function is in this form. So let's solve this equation to separate out real part and imaginary part. We first multiply j omega inside the bracket. So we'll get j omega plus j square omega square into another bracket 1 plus 2j omega. So again we know j square is nothing but minus 1. So I can write it j omega minus omega square and 1 plus 2j omega. So multiplying this bracket inside, we will get 1 upon j omega plus 2 times j square omega square minus omega square minus 2j omega cube. So again we know j square is equal to minus 1. So I can put this is minus 1. So this term will become minus 2 times omega square. So minus 2 times omega square is equal to minus 3 times omega square. So 1 upon j omega minus 3 times omega square minus omega minus 2 times j omega cube. So I can rewrite this as minus 3 omega square as a real part plus j times, if I take j common, what I'm left with omega minus 2 omega cube. So this real part and imaginary part is here, but it's not even separated till this. So what we need to do is we need to rationalize this function by multiplying complex conjugate of this number. So we know that a plus, if there is a term in the denominator, 1 plus a plus jb, so multiplying with complex conjugate in numerator and denominator is like multiplying with a minus jb divided by a minus jb. So we'll do the same thing here. We will multiply with complex conjugate of this number to rationalize this function. So how we are going to do that? We got gj omega h j omega. We got this number 1 upon minus 3 omega square in real part, j times omega minus 2 omega cube. We'll multiply this with minus 3 times omega square minus j times omega minus 2 omega cube divided by the same term. So if you see the multiplication in denominator, and we see this is as a, this has a b, this has a, again this will be as b. So multiplication of a plus b into a minus b is like a square minus twice ab. It's like a square minus b square. So I use the same formula in the denominator, and what I'll get is square of minus 3 omega square, that is minus j times omega minus 2 omega cube square, and in numerator I get this multiplication, that is minus 3 omega square minus j times omega minus 2 omega cube, right? So if I again rewrite this equation as 3 omega square minus j times omega minus 2 omega cube and solve the denominator, I'll get 9 omega raised to power 4 plus minus j square of minus j is equal to, the term will become positive, and we'll get omega minus 2 omega cube bracket square. So here I can separate the real part and imaginary part now. This is kind of real part with denominator, and this will be imaginary part with the denominator. So let's separate this out as 3 omega 3 omega square upon this denominator 9 omega raised to 4 plus omega minus 2 times omega cube bracket square minus j times omega minus 2 omega cube upon the same denominator. So now the transfer function gj omega h j omega is separated out in two terms, that this one is as a real part, real term, let's write here as real part, and this as an imaginary part of complex number. So why we separated out this real part and imaginary part of given transfer function? We wanted to find out the intersection of part 1 of the Nyquist plot with imaginary and real axis. So we already separated out. Now let's understand how we can find it. Let's understand this concept in a quick note. We know that if we consider a complex plane with some real axis and imaginary axis, and there is a point in this complex plane which is represented as a plus jb. If we put a equal to 0, that real part equal to 0, then this number a plus jb will become only jb. That means the point will land up at imaginary axis. And if we put b equal to 0, that imaginary part equal to 0, then that point will land upon real axis, and we will be left with only a. So similar concept we can use here, that to find out the intersection with imaginary axis, we will put real part of this transfer function equal to 0, and to find out the intersection with real axis, we will put imaginary part of the transfer function equal to 0. So let's do it. So first we will put imaginary part of the transfer function. Yeah, that is imaginary part omega minus 2 omega cube equal to 0, that is omega minus 2 omega cube upon 9 omega raised to 4 plus omega minus 2 omega cube bracket square. So if we put this term equal to 0, this denominator will go to right hand side and become 0, and we will get to omega minus 2 omega cube is equal to 0, that is omega equal to 1 by omega square will be equal to 1 by 2, and therefore omega be equal to 1 square root of 1 by 2. That, and we know square root of 1 by 2 is nothing but 0.707. So we get what we did here. We equate the imaginary part of the transfer function equal to 0, and we got intersection with real part. So this is omega, where we will get intersection with real axis. So we find exact point where it is intersecting with the real axis. We'll use the magnitude equation, that is 1 upon omega square root of 1 plus omega square root of 1 plus 4 omega square. That is equation number 2. We'll put this value of omega 0.707 into this equation. So we'll get magnitude 1 upon 0.707 square root of 1 plus 0.707 square to square root of 1 plus 4 times 0.707 square. So if I solve this equation, I'll get value of this magnitude as 0.66. So the intersection with a real axis is at 0.66. So let's draw this intersection point here. So this point is minus 0.66. Now once we got the intersection with real axis, in next slide we will find out intersection with imaginary axis. So how to find out the intersection with imaginary axis? We'll put a real part of this given transfer function, which is separated out, is equal to 0. So the real part here is, we highlighted it. So 3 omega square upon that denominator. So we will equate real part equal to 0, that is minus 3 omega square upon 9 omega raised to 4 plus omega minus 2 omega cube bracket square equal to 0. So denominator, when it goes to right hand side, it will become 0, and minus 3 omega square will be equal to 0. So solving it, we will get omega equal to 0. So if we put this value of omega into our magnitude equation, m equal to 1 upon omega square root of 1 plus 4 times omega square root of 1 plus omega square. Sorry to rearrange it. And when we put omega equal to 0 in this equation, we will get omega magnitude at infinity. So this plot is intersecting the real axis at infinity and at omega equal to 0. So this point we already know in our given plot. It is here at omega equal to 0, that magnitude is at infinity. So this point is intersecting is here. So now we'll go to our next part, that is part number 2. That next part is a semicircle with r, and that radius r is equal to e j omega, where r is tending towards infinity and theta is varying from plus 90 degree, here towards minus 90 degree. So how we are going to find out the mapping of this entire right hand plane to the some W plane and find out the Nyquist plot for the same? It's very simple. We do have equation in the form of transfer function. We put S is equal to R times E j theta into transfer function. So what was our transfer function? G of S into H of S is equal to 1 upon S plus 1 upon S bracket 1 plus S and 1 plus 2S. So putting into this, the transfer function will become e raised to j theta in this form, and we get 1 plus r. So if we take out r e raised to j theta common from first bracket and 2 times r e raised to j theta from second bracket, we will get 1 upon r cube e raised to 3 times j theta into bracket 1 plus 1 upon r e raised to j theta 1 plus 1 upon 2 times r e raised to j theta. So why we did it because the r is tending towards infinity, and if you want to put this r radius r tends to infinity, we need to put limit r tends to infinity in this equation so that we'll get entire graph for the same. So let's do it. So r is tending to infinity and theta is varying from plus 90 degree to minus 90 degrees Celsius. So let's put limit r tends to infinity into gj omega g r e raised to j theta into h r e raised to j theta form. So this will become limit r tends to infinity 1 upon 2 times r cube e raised to j 3 theta 1 plus 1 upon r e raised to j theta 1 plus 1 upon r e raised to twice r e raised to j theta. So if I put r equal to infinity directly, what will I get is one thing I can do is e raised to j theta can be taken into numerator and it can be written it as e raised to minus j 3 times theta, and we will left with 1 into 2 times infinity cube 1 plus 1 upon infinity 1 plus 1 upon infinity. So this denominator entirely will become infinity. So 1 upon infinity will be 0. So the magnitude will be 0 and the direction will be e raised to minus j 3 theta. So for this part 3, for this part 2, I get a curve with magnitude 0 and the direction or a phase equal to j times 3 theta. So we know here that theta is varying from plus 90 degrees Celsius to minus 90 degrees Celsius. So the phi will then become minus 3 times j theta, that is 270 degrees Celsius, and minus sign will be there, minus 270 degrees Celsius to minus minus plus 270 degrees Celsius. So what I'm doing, I'm putting theta into this equation, I'm getting the phi angle. So for the part 2, what I'm getting, a graph having magnitude 0 and direction. So the direction with minus 270 to plus 270. So this is a 1.5 circle with magnitude equal to 0. So I can plot this part into our Nyquist plot, and this part will start as part 2. So after completion of part 1, this is starting at this point at m equal to infinity. So in the graph, same mapping will be there. So at omega equal to infinity, this part will be here, and here I'll get two semicircle at the origin with obviously magnitude, that is radius 0, and anti-clockwise semicircle, that is 1, again one anti-clockwise semicircle 2, and again one anti-clockwise semicircle, 3 anti-clockwise semicircle, that is 1.5 circle of magnitude 0. So this is actually a magnitude that is radius 0. So it's very small, and even if you don't draw it, it will be okay. But we know this part will exist here for mapping entire right hand plane. Okay, so this is done. Now we'll jump to our next part, that is part number 3. So part 3 here is where it's mapping from minus infinity to 0. This particular part number 3, is where omega is varying. Omega is varying from. So in part 1, omega was varying from 0 degree to minus plus infinity, and part 3 here is varying from minus infinity to 0. So part 3 will be exact replica, or let's say inverse, of part 1. So you can see it here, this part is and this part are exactly a replica to each other. So the Nyquist plot obtained in such cases will also be the replica. So how we are going to plot part number 3? It's a replication of part 1, and it will start from the end point of part 2. So it will start from here. Let me draw it with green color. It will start from here, and it will look exactly same replication of this. It will go till the point where magnitude becomes minus infinity and omega becomes 0. So at this end point, we will draw part 4 from this ending point. So to draw part 4, we need to do some more mathematics. Let's do part 4. So how we are going to plot part 4? It's a part having a radius r, e raised to j theta, where r is tending towards 0 and theta is varying from minus 90 degree to plus 90 degree. So we put S is equal to R e raised to j theta into our given transfer function. So the transfer function g will become g of small r e raised to j theta, h of small r e raised to j theta equal to 1 upon r e raised to j theta 1 plus r e raised to j theta 1 plus 2 r e raised to j theta. So when we put limit to this part, we will get limit r tends to 0 into this part, we will get part 4. So part 4 will be equal to limit r tends to 0 1 upon r e raised to j theta 1 plus r e raised to j theta 1 plus 2 times r e raised to j theta. This will become e raised to minus j theta into 1 upon 0, that is infinity into e raised to j theta. So part 4 here is a mapping where it's a mapping where is having a magnitude of infinity and direction or phase, that is e raised to minus j times theta. So obviously infinite magnitude will be coming from infinity, and the phase here theta is varying from minus 90 degree to plus 90 degrees. If we put this theta value into this form, then the phase I'll get is plus 90 degrees Celsius to minus 90 degrees Celsius. So this will be a contour. Part 4 will be a contour with infinite magnitude, and it will start from minus 90 and it will end at minus 90 degree. So let's plot it in our graph. So the graph will start from plus 90 degree here and end at minus 90 degree here, and having magnitude infinity and infinity. So the point having magnitude infinity and plus 90 degree angle is here, and the point having minus 90 degree phase and infinite magnitude is here. So this part will start from point A and end at point B. So let me draw it. Okay, so let's look into this graph one more time. The part 1 is here, where it's starting from this point and ending at origin here. If I zoom into this origin, I see that at the end of part 1, the another part is starting, and it is an anti-clockwise circle, 1.5 circle, that part 2 is ending, and the green color is part 3, which is starting from the end of part 2 and is going towards infinity. And at the end, I'm getting part 4 from end of part 3. Let me rename it part 3. And part 4 will begin here, that is part 4. This is the contour. So this is the Nyquist plot for given problem. So the direction is here. It is coming from part 1 is coming from infinity minus with magnitude infinity from minus 90 degree Sorry, the direction is in following way. The part 1 is coming from plus 270 degrees Celsius, and it is coming towards origin from minus 270 degrees Celsius. So it is the end up here. Then the second part is starting with anti-clockwise semicircle and is going in anti-clockwise from minus 270 to plus 270. And at the end of first second part, the third part is starting, which is starting from this and ending at this point with magnitude infinity and omega equal to 0. So that part is starting from minus 90 and going towards plus 90. And the last part is going in clockwise direction, that is from 90 degree towards minus 90 degree with the magnitude and phase. This is entire Nyquist plot for type 1 system. So let's define the closed loop stability of the system using this Nyquist plot. So to define stability, you need to remember only one formula, that is Z is equal to P minus N. What is P? P are poles, not only poles, P are right hand side poles of open loop system. So our open loop system G of S, H of S is 1 upon S, 1 plus S, 1 plus 2S. So this system is having no pole on right hand side. So the value of P is 0. Then what is N? N are circlements, N circlements to the point minus 1 plus 0 times J. So how many circlements are there to minus 1.0 minus 1 plus 0j in our graph? Let's see the graph. So the 0.66 point is here. So according to that, point minus 1 will be here. Minus 1 plus 0j. So this point, for this point, we don't have any encirclement by the Nyquist plot. So the value of n here is 0. And what is z? Z are right hand side poles of closed loop system. So that can be calculated using this equation. So z is equal to p minus n, that is 0 minus 0 equal to 0. So the value of z is equal to 0. So there are 0 right hand side poles of a closed loop system. Hence, the closed loop system is stable. So we started with the open loop transfer function, and we draw Nyquist plot for this open loop transfer function by variation of omega and that contour with a capital R radius and small r radius, and again fourth part is small contour, the contour with omega variation from minus infinity to 0, and we got a Nyquist plot, and if that Nyquist plot is encircling, we got some value of n, and depending on the n, this n, we define stability of the closed loop system. So from starting with the open loop system and defining stability of a closed loop system is what we can do with this Nyquist plot. Thank you everyone. Please like, share and subscribe to our channel. Thank you.